So today I will tell you about our experience with Akka and Kafka streams. So I guess their main differentiation from things like Spark and Flink, which also do streaming, are that they actually libraries. So you literally start your own JVM processes, call some functions, and then they do stream processing for you. While things like Spark and Flink, they are like cluster computing frameworks. You deploy something everywhere, and then you call some API and submit stuff, and then they do something smart. Spark, at least the open source Spark, is also a bit high latency. So like open source Spark streaming can do maybe latency half a second. Flink is better. So the good thing about Akka streams and Kafka streams is they are very lightweight and also pretty low latency. So hopefully these examples of possible stream processing use cases are familiar to you. So in very generic terms, you have some streams of events you want to process, and maybe you want to filter out some events, maybe you want to transform them. Then another common use case is actually deduplicating. So basically the event stream comes in, there are some messages with keys, and you want to keep for each key only one first message which arrived. Another is aggregate, where you want to compute basically some kind of streaming count of things identified by a key. Like the classical example is word count, where you get some strings coming in and split them to words, and then you count how many times each word has been seen so far. Another common use case is joins. So you have two streams, maybe they tell something different about the same user, so you want to join data from two streams into some kind of common object, do something with it, and then publish it into another stream, or maybe write to some kind of data store. And there is something also called windowing, which is kind of like aggregation. So the idea is basically that you denote some kinds of time-based windows in your series of events associated with, for instance, one user session. And then you do some kind of computation for each window separately. Like there is lots of like fancy semantics around it. I think it originates originally from Google. So if you're interested, check this out. So the typical challenges for stream processing. So first question is like, do we do at least once processing, or maybe it's possible that we will see the same message twice, or publish the same message twice? Exactly once, which may or may not be a requirement for you. And in more fancy use case, like if you're publishing to two topics, two streams, related messages, you want to make sure that they get published to both topics, or don't get published at all. So it's called transactions or atomicity. And Kafka actually supports that. And yeah, unsurprisingly, there's latency. So I guess on Java, 10 milliseconds latency is very good. So latency is the time between the event comes in until it gets processed and the side effects propagate. 100 milliseconds is kind of good, and maybe second is what Spark streaming does. So in many use cases, that's sufficient. So it depends on your use case. Probably if you want to go under 10 milliseconds, then you should be using something else and not Java. Fault tolerance. So like if you have multiple machines processing some partitions of your stream data, so if one of the partitions actually dies, or the node which processes the partition, you want to recover a new node which will continue processing in the same state, so that, well, you don't have to restart for the process. And finally, the one interesting thing is called back pressure, which I will talk to you about now. So who actually knows what is back pressure? All right, cool. So in very general terms, what happens is that if you have a producer and a consumer, and the producer is faster than the consumer, then your messages will start piling up. And there are a couple of approaches how we can solve it. So in reactive streams, how many people know what's a reactive streams approach? Cool, less, but still cool. And Akka streams, which is kind of compatible with reactive streams. And who knows what is Java 9 flow? So now in Java 9, there is reactive streams copy-paste called Java 9 flow. Now you do. So basically, it's a mechanism which allows you to communicate between a producer and consumer. I think in general terms, it's called push and pull. It's very common. And what happens is basically the consumer tells the producer like how many messages it can consume now. So please don't send more than 100 messages. And this is called pull. And then the producer has the right to push up to 100 messages. Or maybe if the consumer called your pull method twice, like pull 10 and pull 15, then the producer is allowed to push up to 25 messages. The whole point of this story is that if you do that, then the buffer needed to keep the messages between the producer and the consumer is limited by the difference between how many messages have been requested minus how many messages have been processed. In Akka streams, which is purely in-memory framework, it actually is important because your buffer would grow in memory and it would eat up all your Java memory. So all kinds of other frameworks like reactive streams, RX stream and whatever are the other fancy things, they all need to somehow tackle this issue that the buffer is in memory and you want to limit its size. And so somewhat different approach is taken by Kafka. So we'll talk a bit more about Kafka later, but in a very abstract term, Kafka is just a sequence of messages literally written into a file or a sequence of files, like sequentially, and then that's what the producer writes to. And then there is a consumer which says, I want to read messages starting from this offset. And that's pretty much what Kafka does. And so in this case, basically, okay, there is some limit to the buffer, right? So at some point, your disk will end and problems will appear. But the presumption is that, well, that's how you approach it. So basically, producer produces messages as fast as it can. It writes them to Kafka topic, and then the consumers consume them, well, as fast as they can. And, well, maybe there is like spikes of events. So at some points, there will be more events in your topic. But the hope is that the steady state of processing messages is such that consumers see messages, eat them faster than the producers can produce. And Kafka also has some methods to actually forget about old messages, but hopefully you get to read them before it forgets them. And any questions about back pressure? Anybody understood what I said? Okay, so the same hands who basically knew what it is. Great. So that's how reactive streams interface looks like. In very simple terms, do I have a mouse? Apparently I don't have a mouse, but I have a hand. So this is the spool method. And so the consumer can say that, well, I want to get like 10 more messages. And the idea is that this method is actually non-blocking. So you say, I want 10 messages, and then keep on working. And the producer gets this interface, and well, it is allowed to basically produce using method on next, the next 10 messages. And the idea is that, well, ultimately there is this publisher interface. It is called with subscriber, and subscriber gets method on subscribe with a subscription. And so that's how publisher, producer, and consumer get to communicate with each other. In case you didn't understand anything, there is actually a picture. So it says the same thing. So we have a publisher. We subscribe to it using a subscriber. After that, the subscriber gets a subscription with method onSubscribe. And then periodically it says request. And well, the publisher gets to basically call onNext to produce messages. And this is very useful and important primitive, which is used in pretty much all reactive systems in some way. Before we go forward, does anybody have questions? Cool. So, Akka streams. There are two kinds of interfaces. The simple DSL, or domain-specific language, is a linear one. So you have a source, it produces messages. You have a flow, which processes the messages. You can basically chain multiple flows in sequence. And then there is a sink where the messages go. I'll show you some examples. And then there is a more fancy graph DSL where you can actually like create arbitrary processing graphs with forks, joins, and all kinds of interesting things. I have to admit that like, the amount of primitives in Akka streams is huge. So like anything I can think of is there. So if you think of it, these interfaces are just for sequential composition, but in Akka streams you can build all kinds of fancy parallel processing schemes. And they all get compiled to the regular Akka actors. Actually, it's called materialization. However, Akka streams doesn't have any persistent state. So what happens is that if you restart the application, then unless you brought your state somewhere outside, your state is gone. And basically it's compatible with reactive streams spec, so it can integrate with any other framework which supports reactive streams. It is compatible with Java 9 Flow, and pretty much has integrations with any possible like data store, or streaming system, or Kafka, using a framework called Akka. And the nice thing about Akka is actually, I think like Akka itself can do like tens of millions of messages per second. Let's say your throughput will probably be less because it will be bounded by external systems. It's not the Akka streams which will be slow, but the systems with which it's interacting using sources and sinks will bound your latency and throughput.
This latency of 10 milliseconds, is it inside of the JVM?
Yeah, sure. It's like between sources, right? The sinks. So if you call something outside, right, then...
It seems that inside of the JVM you could do better, but...
let's put it this way, probably it's less, but it depends on the use case, A, and B, until garbage collection kicks in. So I think if you wanted less than 10 milliseconds in Java, you're probably doing something wrong. So maybe on average it kind of is, right? But I don't know, maybe you disagree. Yeah, and so here are a couple of examples. So one example, so this is actually Scala, which is like a nicer version of Java. According to some people. Yeah, somebody wanted to ask something, I think. Or no, okay, cool. Yeah, so here is one way to define a sequential flow. So you have a source. It can read from anywhere. Here it just produces numbers from 1 to 6. Then you pass it through a flow, which in this case multiplies it by 2. So this is a shorthand for writing lambda function. So this is basically the argument. And then, well, you basically call to a sink, and the sink can be anything, like a Kafka topic or a file. In this case, we literally just call for each. And, well, basically, DSL allows you to compose things in different way. You can start from source and then basically go forward. So basically, you define something in the beginning, so read it here, I guess, and then chain things up. Or you can start from a sink and then start chaining back to the beginning. The difference is basically, in one case, all your intermediate objects will be sources because they only produce something. They don't have any inputs anymore. Or sinks because they only ingest something, but how they produce stuff already has been defined. And so a more fancy syntax looks like that. So what we're trying to do here is this nice picture. What happens here is we have a source. We have a function which transforms the source messages in the source. We have a broadcast operator, which means that we will be sending all messages in both parallel processing streams. We apply functions F2 and F4. Then we merge these streams and apply another function F3, and then we send it to the sink. And so that's how you define it. So we're building a graph DSL, and you define a source, a sink. You define the broadcast and merge operators. Well, in this case, there are 2 elements in them. Well, you define some transformation functions. In this case, they're just adding 10, but it could be something more fancy. And this is the DSL, which allows you to actually wire up your graph. So, well, literally, you look at this picture, you see an arrow, and you can just write it here. Like the source sends something to F1, one sends something to broadcast, and then, well, broadcast sends to F2, broadcast sends to F4, then we merge, and then F3, and then out. And that's the general idea. In general, your graph might have some inputs and outputs left unspecified. In this case, you can basically reuse it as a block. So you can create a new graph DSL where you will take this graph, and it will be a new operator which you can reuse to build more complicated graphs. Because you left some inputs and outputs open, you can wire them up using, well, the same principle. So I'm pretty sure actually these operators themselves are defined in terms of more simple elements. Any questions so far? Yes.
Can you do loops?
You can, yes. But you have to be careful, because if you do them wrong, then...
Infinite loops, yes.
So basically the thing is that there is back pressure, right? And so if some buffer grows to the maximum size, which is by default only 16 elements, you can change it, right? By default, each buffer between each two stages is 16 elements. So if you do something strange and the buffer fills up, and there is back pressure, and so the producer in the loop can't produce something, and the consumer can't produce, you're stuck. But there are ways around it. There are, for instance, merge operators, which always prioritize one of the sources. And so it works out. But again, probably there are valid use cases for loops, but...
Will it block or discard messages when the buffer is full?
You can define back pressure strategies. So default is block, but you can say drop. You can say drop new and drop last. Let's say any kind of pattern I can think of, it's there. So it's actually very fancy, I have to say. Maybe sometimes a little bit hard to get into because it's so complicated if you start to do some fancy things, but it pretty much has everything. As long as it's dies with the JVM, right? So there is no state. Yeah, so here is an example of actual integration with Kafka. So what happens is that, so the Alpaca project is Kafka Streams integration project with pretty much every kind of topic queue database. And so the magic that happens here is that, unfortunately, I will tell you about what is on commit in Kafka later, but let's put it this way. We have a source in the Kafka which subscribes to the topic number 1. And so what happens is that it will be receiving events from this topic. Now, we want to actually process these events, this message, using a business logic method. But this business logic method is pretty long, and it takes some effort to, like, it actually takes some time to do. Or maybe, I don't know, it does actually some blocking operation, which is a bad thing, but it's a real world, so it might happen. So what you want to do is you want to actually run this business logic method in 10 parallel, well, in practice it's actors, but you can think of it as threads. But this operator actually guarantees you that the outputs of these business logic calls will be in the same order as they came in here. So you get parallelism, but it preserves the order, which is kind of nice. Okay, and so the business logic, basically what it does is that you call the business logic using the record, which has key and value, from the Kafka. What I didn't tell you is that in Kafka, all events or messages have a key and have a value. Like what you do with them, it's your choice, but like it's basically like the assumption. You can put null in your key if you want to, but it's there. And the business logic actually is a future. And so you need to tell what this future, like basically we want to do some transformation on the future. So we call the map function on the future, and what it does is that it replaces the output, the done, with the offset of the message in the Kafka topic. So like I mentioned before, Kafka topic is a sequence of messages. Each of them has like an offset or a number, right? And you keep track how many messages you have processed by literally knowing like the sequence number. And so, well, basically after having processed this message, you get this offset. And then the next step is what you do is you essentially use the DSL to commit the offset. What it means is that you write in Kafka in a certain place called consumer group, but this consumer for this partition has read up to this offset. So if you restart this application, you will start getting messages only from this offset. So that's how you basically get the persistent state, which otherwise wouldn't be in Akka streams application. And yeah, well, then you actually say that you don't want to have any meaningful sync. So you say sync ignore. And technically, once you have created this thing, you actually have to materialize it, which creates a bunch of Akka actors, which will actually run your thing. And like you can, for instance, tell that some of these steps will be running on one thread pool, which is called dispatcher in Akka, but you have really precise control what happens, and by the way, by default, it actually fuses sequential operators so that they run inside one loop and one actor. So if you actually want to achieve pipelining where one operator runs in one thread and the other in another, you actually have to tell it explicitly, because by default, sequential operators will be fused into one. And so what you do is you write here .async, and then it basically introduces the actual buffer between them. So in the most simplest cases, you literally will just have one loop which reads from somewhere, does a bunch of fused operators, and then outputs somewhere. If it's not enough, you split it in the middle, for instance, and you get now 2 threads. So that's how pipelining works. Or you could do parallelism if that matches your use case, like it does in our case, right? So we actually process things in 10 parallel threads. Or actually, it's actors, but they are usually mapped to threads in a dispatcher, which is a thread pool. Any questions? Isn't Scala awesome?
Yes. Yes. Sometimes.
I would say if your code is so simple, why not just write a for loop?
Because it's async.
It
Well,
doesn't.
is it really?
This committing
Okay.
thing is not really simple at all.
I mean, if it's literally a loop, yes, but if it's something more complicated, like parallelism, right? Or pipelining. Or you have
in
to-
Java streams, you just use a parallel stream.
Yeah, I think Java Stream is actually also implementation of reactive streams, right?
Is writing tests more complicated for this type of async?
So they actually have a testing framework where you can generate custom consumers and producers. By the way, now I think of, I don't think Java Streams actually is reactive. Java Flow is reactive. So I need to think of a better answer.
What will happen if you have an error in business?
Basically what happens is that there is a way to add exception handlers, and then you tell, it's a bit like Akka basically. What you can do is you can define a tree of subgraphs. So you have your whole Akka Streams application, which is a graph. Maybe it has a subgraph, right? And you can say that for this subgraph, the policy is maybe restart or propagate. And so that's how you do error handling, basically.
So what about committing offset is error? When you have error, so you're right now committing that offset to Kafka.
It only happens if error didn't happen, right? If error happens, you by default just tear down the whole thing, right? And of course, you have to distinguish between errors and failures. I think failures is what tears down your application. Errors actually by default just is a different kind of message. You can handle it and decide to actually tear things down, but yeah, there is this distinction. Cool. Okay. So we successfully managed to go through the half of my presentation. So Kafka Streams. Kafka Streams is technically also a library, but it is very tightly integrated with Kafka. So it has very different properties, although sometimes it looks similar. What it does is basically, in very simple terms, there is a bunch of Kafka topics with partitions. There is an application. It's your job to fire up this Java application, but it will consume from these Kafka topics and produce into new Kafka topics. Now the question is how you define the application. And it's also a question that if I have a topic with multiple partitions and you fired up 3 copies of your application, you need to decide which partitions are processed by which copy of your application. So this is done using something called Kafka consumer groups, and it's pretty much like hidden from you. And so one very nice thing, besides the fact that actually you can do all kinds of joint forks and aggregations, is that it actually has a key value store, which is on one hand in memory, so it's super fast, right? The latency is very low, but it's also persistent, so it's RocksDB. And most importantly, it's persistent and replicated in the sense that, let's say you have one processor or one partition, it has in memory key value store. If this key value store actually dies, you can fire up another application, And all updates to this key value store were actually written to a Kafka topic. And it can basically pick up from that Kafka topic the contents of this key value store. Even more so, you can do it before the first application crashed. You actually can say that you have a hot replica. It reads the updates to your key value store from Kafka topic, and when it actually dies, you just fire it up and it's there. And you would think that probably this means that your Kafka topic grows forever, right? Because like every update is the same key, and you write to Kafka. The thing is that actually Kafka has always had a very cool feature, namely, if you can configure Kafka topics so that if you write two different keys with the same with some values, and after something called compaction, it keeps only the last key value pair. And essentially, it's not organized as a key value store, but it can be thought as basically like a transaction log for a key value store. And they actually are very proud. The Kafka people are very proud of this concept, and I think there is good reason for that. It's a great idea.
Can compaction be done while you're writing to the
Yes.
queue?
So in a way, it's like a log-structured merge tree, where the way basically like all contemporary key value stores work. But like it's just that the main use case you optimize for is for writing, right? Like you literally read sequentially and then get it into a key value store and then work with the key value store. Yeah, and so probably like you can get the throughput of like 100,000 messages per second per partition. You might get to 1 million, but I don't want to promise it to you. So it depends on the use case and the setup and so on. And Kafka supports transactions, right? So you actually can write to multiple topics atomically. So you either messages appear in both topics or they don't appear at all in case of failure. If you use transactions, your latency will be definitely 100 milliseconds and throughput will be lower, but not terribly so. If you don't use transactions, well, you can basically play, like you get lower latency with lower throughput, or you get higher latency with more throughput. So there are like parameters how you can configure it, which is again pretty cool, I think. Now I have lots of pictures. I heard people like pictures. Or maybe you have questions.
Cat pictures, I hope.
Sorry?
Cat pictures.
No cat pictures. I used to have Star Wars themed pictures, but I don't do this anymore. I'm boring. Any serious questions? Okay, so this is hopefully something you have seen before. So we have a topic, it has some partitions. Each partition has a sequence of messages. And so every time you write a message, it gets like the next sequence or offset in this partition. And so here how the Kafka consumption works. So you can have multiple consumers. They can read from the same Kafka partition topic of a topic, but they each have a different offset, and that's actually how they decide where they read from. And yeah, there is no coordination in that sense between the consumers, but consumers in one group can decide that this consumer reads from this partition, and this consumer reads from that partition. And that's how, within a consumer group, you can coordinate reading from topics. But if some other consumer group decides tomorrow that they also want to read from this topic, well, they will just set the offset to something. They can set it to 0 or last, or say that give me offset for yesterday 1 a.m. and just, it will tell you what was the offset at that time, and it will keep reading from there. Hopefully.
If you use partitions, is it transparent for producers? So.
Let's say it is, but you should really think about it, because the reality is that the partitioning principle, right? Yeah, you want to basically to define some partitioning principle which is related to your business logic. Like you want to basically make sure that all messages about the same person go to the same partition, because it will be processed by the same partition processor. And so if now messages about the same person are in two different partitions, well, you're kind of screwed. And so what typically happens is that you have some kind of business or entity key, you take a hash of it, and then you, like, I don't know, do model 16, and it gives you 16 partitions. And so, again, even more better, colorful picture. So that's how the topology looks like in a very abstract term. So what you have is you consume from some sources which are pretty much only Kafka topics, and you have a bunch of these gray bubbles, which are processors. There is a sink, which is also actually a Kafka topic. And, well, pretty much these blue arrows, they actually go down. It doesn't show, but the data flows down. And the way Kafka works is that to you, it looks like you're processing messages one by one. So all the buffering is completely hidden from you. But let's say it reserves the right to do buffering and optimization behind the scenes. But it doesn't give you, let's say, any callbacks to that. So basically, you can tune some things like, do you want transactions or not? But let's say if Akka streams, you can basically do anything. It's a toolkit. You can put together a bunch of small things and get exactly what you want. Here, the number of knobs is much smaller. And so another cool picture is that, so what we have here is we have a Kafka topic with a bunch of partitions. So each partition is processed by one task. And as you can see, each task is, it has exactly the same application, right? So this topology is exactly the same. So they are doing exactly the same thing, but on a different partition of data. And there are the state stores, which I mentioned about. And state stores are also partitioned by the partition which is being processed by a given task. And, well, ultimately, the tasks are also mapped to threads, so one thread can run multiple tasks, but it doesn't have to. And in principle, the threads can run on multiple machines. And the way it works is that you can fire up more instances of your application on new machines, and it will allocate some of the tasks to these new instances. So you can do it on one JVM slower, or you run 10 JVMs on 10 machines, and you can do it faster. And yeah, in the end, you produce data to Kafka topic. So a more lower level Kafka interface is a consumer and producer. So, well, Kafka streams builds on top of that interface. It's really just a producer publishes messages, and it can buffer them before sending out. And the consumer knows what offset you're consuming from. And there is an optional feature where you can say, what is the data format of your data, the schema. It's actually our schema, and they actually even have schema registry. So you can say that messages in this topic have schema with this type in schema registry, and you can even version it. So there is something fancy about that. Never use it. Any questions about this picture?
The back pressure idea doesn't really apply to this because it flows from top to bottom.
So let's say whenever it's needed, it will insert a new topic. So actually, Kafka streams can create internal topics if it needs to. So you have input topics, output topics, and if it needs to, it puts internal topics inside, right? And so if your buffer is unlimited size, then there is no pressing need to have a back pressure. But I'm pretty sure that actually in some components of Kafka streams inside, they use some mechanism for back pressure to basically make sure that producers and consumers have the same rate. But they don't expose it, so there are no knobs for that. You can say pretty much like how many messages have to be consumed from a topic before it's all pushed out to the output topics. But that's pretty much what you can do. And there is a concept of transaction, so you can say that the transaction spans 10 input messages or something, and the messages produced by these input messages. So that's the level of knobs you have.
You mentioned very briefly about the schema registry.
Mm-hmm.
Does it have some sort of an external API, or is it based on like the Confluence's version, or is it entirely on its own from Kafka? Where does it come from?
So I think it's an open source project, and it's definitely supported in all possible ways by Confluent, right?
So it's related.
Yeah, it is. And so the way it works is actually it keeps all its updates to the registry in a Kafka topic, obviously. And there's an REST API which basically serves you these schemas. It's not a very complicated thing, right? But everything is Kafka topic in Kafka world. Where do you think offsets are stored of Kafka topics? Right, there is an offsets topic. where do you think transaction information is stored in Kafka? Right, there is a transaction log topic where the transaction coordinator for each partition stores information about the transaction.
It has to end at some point.
No. Any more questions? Cool. Yeah, so one thing I wanted to talk about is partitioning. So if you have a task or an application which joins two streams, then these streams have to be co-partitioned. What it means is that they are partitioned using the same scheme. And more specifically, let's say we have Kafka topic A and B, and let's suppose that somebody actually applied the same partitioning algorithm to decide which message goes to which partition. In this case, basically, as you can see, this task consumes messages from partition 0, and this task produces messages from partition 1. So basically, every time your topics need to be joined in some way, you have to either make sure they are already co-partitioned or repartition them, which basically means creating a new topic where you rewrite things and it's partitioned the right way. So, important concept. So I think actually, even if you don't use Kafka streams, these patterns are very useful because you can also do it in Akka streams. You can do Akka streams application using the same approach on top of Kafka. And also Kafka streams works only with Java, but if you decide to do it in some other language, you can probably like borrow lots of ideas from this approach. So I think it's like a great philosophical framework for building complex data processing applications, which originates from LinkedIn. Anybody has questions about topics? Cool. Finally, I have some code. So the classical example, so what we have here, so we first create a stream which reads from this topic called text lines. And technically, each stream has a key type and value type. In practice, we don't care about the key type. We only want the values, right? The text lines. And it's a case stream, right? And by the way, that's Java. No, it's actually Scala. Sorry, I wanted to say that's why it's ugly, but probably... Damn it, I shouldn't work in marketing. Yeah, so what you do here is you take the text lines, right? This one. From here, and you apply something called flat map. And you apply flat map to values, so you don't care about the keys. And what flat map does is that you first take a string, you split it into words, make them lowercase, right? And each flat map basically gives you a sequence of words in that string. But what you want to produce from that flat map is actually a flattened sequence where you first get words from the first string, then words from the second string, and so on. So that's why it's called flat map. If you had just map values, then you would get a sequence of sequences of words. And so that basically flattens your sequence. Hopefully I'm telling the obvious things from functional world. How obvious is flat map? Who doesn't know what is flat map? Nobody admits. Good. And so flat map is still a stream. But what you do now, you do group by, and you group the stream by word, and then you do count. And as a result, you create a materialized store, which keeps for each word a counter how many times it was seen so far in the stream. And even more so, what we can do is that we can say that please publish updates to this store every time there is a change to the store to a new topic. So every time a new word appears, we increment the counter, and then we publish to this output topic a pair or a key value of this word and a new counter. And as you might guess, now that you have this topic, A, you could also use compaction on it. B, you could actually materialize it into a Postgres or something else. It's up to you. Any questions about this example? Isn't the Scala beautiful?
So, but this flat map values, this is all just, it happens like in the JVM, and then it's materialized to Kafka, right?
Let's say it might create internal topics if you repartition things, but as long as you don't repartition and don't create materialized stores, it happens inside JVM, inside one partition. task, right? So the moment you need to basically cross the partition boundaries, or you actually want persistence, then a topic is created.
Are these all synchronous?
So it's a good question. They do not say exactly.
Well, what I'm asking is that, can I write an asynchronous function, for example, for flat map?
I don't think you can. So literally, if you look at this picture, then so you have one thread which blasts through your partition. So if that's not the case, maybe you should basically partition it more. At least I don't know the answer out of my head. Maybe there is some solution for that, but I don't think so. Like, it's literally like you can process multiple partitions on one thread, but you cannot process one partition with multiple threads. Any more questions?
Well, you can, if you take like from one partition, you take a huge slice and you parallelize processing of that slice, then you can create some sort of asynchronously in that. But
Sure, you will need to repartition basically, right?
no, but I mean, like if you have a bunch of messages that are not related to each other, then you can just parallelize the processing.
You're right. Yeah, probably there is some kind of map async. I just don't know it off the top of my head.
But in other frameworks, you get to get closer to the knobs, basically.
Yes, so Akka streams, right?
Yeah.
Map async. But what you can do here, you can basically say repartition to smaller partitions, and then each partition will be running on a separate thread. At least, maybe there is some other way. I just don't remember it. So just to remind you, so we have state stores. Each state store is associated with one partition of co-partitioned input topics. So we had two partitions, right? So we have two state stores. And again, another picture to remind you, we have updates which go to the state store. Each update goes into a topic which says that, you know, this key was updated to this value. And you can have ultimately as many consumers as you want who read these updates and create new key value stores. And it's actually, this pattern is called the change data capture, and it can be used in very different situations. Like, for instance, there is a framework where you take Postgres, you keep writing into Postgres, and there's another application which reads the Postgres transaction logs and pushes the updates to the Kafka topic. And then you can process. You can be joking, but it's actually what they do, because you have like a Postgres, which has very specific properties in terms of scalability of reads and writes. So what you do, like, it's an OLTP database, right? So reads are not very scalable on Postgres. So what you do, you read the transaction log, you push it to Kafka, and then maybe you push it to Cassandra. And voila, now you have like very scalable read system. So they actually do that. It's also a very simple way how you can get through the boundaries of organization. So if there is one dark room where people manage Postgres, then you can say, by the way, can we read your transaction log? And you can read their database. Yeah. And so, like I said before, you can compact these things. So if the same key has multiple values, then after compaction, only the last value will be kept. So it doesn't grow indefinitely. And it is partitioned. So each partition will have a separate partition in the topic. So I have one more beautiful picture. Like I said, the Kafka streams pretty much works only with Kafka topics. You can read from Kafka topics and can write to Kafka topics. You kind of can do write to external systems, but you really, they make it hard for you. You can, but like it's up to you. So what you do really is that there is a separate framework called Kafka Connect. And what it does is that it allows you to connect to any kind of data source, very often using this change data capture mechanism. It writes the events to Kafka topic, then you do some Kafka streams processing, and then there is a data sync using Kafka Connect again, which writes it, well, anywhere you want. So it's a bit like Alpaca in Akka streams. Here it's Kafka Connect, which allows you to integrate anywhere. And I have this cute picture. So you have connectors. Some stuff goes in, some stuff goes out. So you have some producers and consumers, which are like the default APIs for reading and writing to Kafka. And finally, you have some Kafka Streams processors, which again manipulate some topics. So I think that's the grand vision of the Kafka world. I actually have 2 more slides with some practical use cases of the theory, but maybe you have questions. Cool. So what we do with this stuff, we are ingesting lots of IoT events from devices, and they come into a Kafka topic. And what they do is that we have a Kafka Streams application which takes these events. It has to deduplicate them. It has to pseudonymize them. It has to transform them into some output format. And plus, we also need to support something called forget. So if there was a device which is associated with a person and it produces a bunch of events, then we actually need to create intermediate ID, which is completely uninformative, like a random string. And we store the mapping from the device ID to this unique ID in one place, and from unique ID to actual events in another place. So when you read events, you actually see this uninformative ID which doesn't link to a particular person. And then there is another GDPR magic where you actually have to be able to forget about this link. And so, well, what we do is basically, because Kafka Streams application has a store which keeps this mapping, we actually send Kafka Streams on another topic message, please forget about this user. And then it is removed from this Kafka Streams key value store. I actually have a nice picture for people who like pictures. I'll just finish reading this slide to you and then show the picture. And then because Kafka Streams is not very good for actually interacting with the external system, we actually have an Akka Streams application with Alpaca, a bit similar to what I showed you, which actually batches the events together and writes batches plus some statistics and summaries into HBase. And we have Kafka Connect, which exports the transformed events from Kafka to S3 just for further processing, backup, and so on. And so here it's a nice, beautiful picture. So events come in. We have Kafka Streams application. Well, let's say this is the pseudonymization store. It has a mapping between the real device ID and the random ID. So if a new device ID comes in, which we haven't seen, we generate a new ID, we store it here. And because it's a key value store, the updates actually go to a Kafka topic. And we do some deduplication using a state store, and we produce the transformed events, which are pseudonymized and deduplicated and transformed. Then there is an Akka Streams application, which reads, well, basically both of these topics and updates corresponding tables in HBase. And finally, there is a separate topic called deletes, which tells you, please remove this link between this device and unique ID from the pseudonymization store. So that's how we do it. That's my last slide.
Woohoo.
We still have 6 minutes for questions.
GDPR question. So the Akka application is actually deleting stuff from HBase as well.
Yes, yes. So basically the delete is a key with a null. An update is a key with a value.
Okay.
And the compaction eventually will remove key with a null from a topic, but there is a retention period. You can say, please keep it around for a week and then just remove it.
What kind of events are these?
Krista, tell them. The secret.
Let's say you have a bunch of devices in your home that measure your temperature, your humidity, how many thieves happen to be in your house at any given point in time. So we like to report these events. There's a pretty large number of different devices.
Yeah.
Can you tell us about operational effort that Kafka requires? Like, how configurable is deployment is? Is it possible to monitor the system? Like, how to trace the requests?
So there are 2 ways to do it. The The expensive way is that you buy Kafka Confluent Enterprise package, and you pay them a lot of money, and they give you fancy tools to do that, like a monitoring application and all kinds of stuff. But there are also open source options which work okay. Some people say that Kafka does run inside of Docker. It technically does run for sure. Like, the question is how well it runs. Some people say it doesn't work so well. I haven't tested it. I suspect it does, but there is some FUD flying around about that. But I have to say that in general, the system is built in a very reliable way, so I'm sure there can be problems. They are usually quite easy to debug. Compared to like Hadoop in general. Like compared to the amount of tears I had when I had to roll out Hadoop, compared to Kafka is just incomparable. So one thing is that Kafka, I think it stores the topics in Zookeeper. So if you need to have like 10 million topics, then there's another project which is probably better, because the Kafka design is pretty much like almost 10 years old. So, and also if you want to do repartitioning, it's kind of painful because you literally have to rewrite topics. So, but the upside is very high efficiency because it's literally reading from a file. Anything else I want to add? Yeah, that's pretty much it.
Does it run on Kubernetes?
Well, that's the question. Like, I think it should. It definitely does, right? But some people at some point said that the I/O layer of Docker is not so efficient. But please, if somebody knows for sure that it is, please tell me. Then I can tell everybody to use Kubernetes. Because by default, people install databases separately from Kubernetes for some reason.
Just a couple of weeks ago, Confluent released Kubernetes deployment tools.
Cool.
Run Kafka in Kubernetes.
That's true. The question is, do they work as fast for very high loads as non-Kubernetes? Probably it does. I hope so, at least. But you're right, yes. There are Docker images for Kafka.
But if you want to run it all on your laptop, just when you're in airplane, you want to debug stuff, or?
So there are two options. There is embedded Kafka, if I'm not mistaken. So there is like some library for testing, which has Kafka interfaces, I guess. And then some magicians in our company also use Docker, just use Docker Compose. And, like, you know, setting up minimalistic Kafka is actually very easy. It's literally just a folder where it creates subfolders named as topics, and then it writes data to files. So, which is pretty good. So people who wrote it actually had experiences with very huge deployments in LinkedIn. So operations was probably quite important for them. So one thing is that, yeah, well, like I said, basically, if you want to rewrite topics, then operationally it becomes a bit painful. Like, you need to carefully think about migration paths. And what they preach is actually that it used to be so that you have this so-called Lambda architecture where you have a fast layer which does Kafka or some other stream processing, and then writes some kind of serving layer. And then there's a separate process which once an hour produces like source of truth, correctly computed data with delayed, like expensive but correct. Basically, Kafka people say that you can get away with just Kafka. There are trade-offs. Like, clearly, if you have some humongous amounts of data, then pushing this data through Kafka will be slower than pushing it through Spark. But many use cases supposedly can be handled just using Kafka without the slow Lambda layer or batch layer, which is also pretty nice, but requires some planning.
Usually in Lambda architecture or the event sourcing, the events are immutable, fixed. So I wonder how hard was it to implement the GDPR requirement of forgetting? So you change the value and wait for it to propagate through the system, or
so there is this compaction thing, right? Yep. And so you can say that after delete is in the topic, it has to disappear like in 10 days. And I mean, to be fair, probably there is a continuum of GDPR compliance. Probably I shouldn't say more, yes. Like,
specify the time period during which you have to actually delete the things
We cannot approve this message, but technically it might be correct. Some people say, yes. We have a lawyer, he can confirm or deny. Nope, no lawyer.
Where? Who?
But you're right, like if it were some kind of super personal data, then at least people at very large companies like Facebook or Google actually say that they literally go and delete the data, like remove the bits. But it makes the architecture very painful.
Yeah. And not only the personal data, it might be just the views and counts of the actions.
Sure, sure. But I think in most cases, if it's not exactly your medical history, so far it has been applied with the common sense. It is generally a good engineering practice.
I guess it's similar like with database. You are deleting a record, but the data is still there. So there, the deletion happens immediately. Just the data in your file system, it takes time to put it there, but it's the same with error data.
So I guess in HBase we can say major compact. Technically it will remove the data, but it will still stay on disk, right? So like if you actually can read blocks of your encrypted file system, then it's still there. So there are levels of paranoia, I think. We tried not to be too paranoid.
Yeah, there is some pretty clever trickery that you can do with encryption in order to actually make a packet like that.
Sounds like a great presentation topic. So, exactly in 1 hour, as planned. Good, thank you.